So good morning, everybody. I will present the results of the validation exercise for the latest version of ozone and temperature retrieved from MIPAS spectra with scientific level 2 processor hosted at KIT. So it's known as KIT processor, but it's hosted by the EMK Institute at the KIT, and it's jointly run with the EAA in Granada. Yeah. So first, what is new? So the new version 8 MIPAS level 1 spectra, so it is expected that they have the better characterization of the detector agent. So in clear, it means that it's supposed to have the improved detector non-linearity correction. It was there was a try to correct it with the version 7, but it was overcorrected, so the version 8 should be the version. So we expect, it implies that we expect the long-term stability of the version 8 compared to the version 5, particularly in the upper stratosphere. So what have we done new as to the retrieval scheme? So the frequency calibration correction scheme now is made more robust. So we added some additional micro windows to obtain more information from high altitudes. So now we have an LLT parameterization. We always had one, but now we have a new one that accounts approximately for the temperature dependence of vibrational non-LTA populations. So we have also better temperature a priori information for the higher altitudes. So trace gas VMRs from the previous MIPAS data versions are used to model the contributions of interfering species. An empirical background: before it was retrieved up to 58 kilometers, now it's retrieved up to 58 kilometers, before it's only up to 32. So also we have an improved offset calibration correction. Now ozone and water vapor are jointly fitted because due to the significant contribution to the signal in CO2 microwindows. And the forward calculations are now based on the updated spectroscopic data. This is the retrieval scheme. So what is expected to do for the data? So, and what is, we can state that this is improvements. So the drifts caused by the detector agent now are reduced. So this is clearly, in short, this is the version which is good for the trend studies. So HR and RR, so MIPAS record, as I said yesterday, it is divided into two periods, 2002-2004, which we call high resolution, so HR, and 2005-2012, which we call reduced resolution, RR. So it is here in this statement, resolution is a spectral resolution. So, and there was always, so when there was this jump within the record, the vertical resolution from two records, they are different, and so it was always a question to compare between themselves. They should be more or less concordant because it's the same instrument. So now this is improved in this version. They're much more consistent among themselves. Also, much more realistic profiles for the simulations where the temperature profile above the altitude range covered by MIPAS, tangential altitudes, deviates strongly from the climatological mean. So, for example, in the elevated stratopause scenario. Also, because we state that a larger fraction of the retrieval was converged, always good, always more data. So, it should be on the previous one. So three-dimensional temperature fields from the ECMWF ERA interims, they are used to account for the horizontal variability of the temperature. And the main feature of our last version, a tuner-compliant error budget is provided, and random, systematic, and total error components are now included in the data product. So for the educated user, it's like the dream life. So what is shown here on the plot is just an example of the averaging kernels of the temperature retrieval for the northern mid-latitudes. So this was about the temperature processing. So for the ozone processing, so what I expected improvement in the data. So improvement scheme to take into the account the effects of the detector agent in level 1B, so improved detector nonlinearity, it did lead to the less instrumentally caused drift in the retrieved ozone values. Ozone retrieval is based on a better temperature, so it's improved due to the use of the better a priori information, and this is valid especially for the upper stratosphere and for the mesosphere. Also, inclusion of the three-dimensional structure of temperature for ozone retrieval, it led to the errors, reduced errors due to the horizontal homogeneities, and for the ozone, of course, we also have the tuner-compliant error budget. Also, I take this opportunity to advertise an additional product. It existed already for the previous version, so it's a user-friendly product. So if you are non-educated user, you have no clue what the average kernel means, but everybody's on your head saying, no, you shouldn't do so, you should take into account the difference in the vertical resolutions. We have the product which is retrieved not on the standard grid, but also called coarse grid. So the idea is the altitude resolution is entirely defined by the vertical grid. So in clear, you have the retrieval on the grid such that diagonal of the average kernel matrix is equal to 1. So here we have an example. So when you have the standard retrieval on the standard grid, you have the matrices of the average kernel like this. It gives you the altitude resolution like this, and for one orbit, it gives you the ozone values like this. If you do the retrieval on the coarse grid, the diagonal of the average kernel is equal to 1, altitude resolution is divided by the grid, and you end up for the same orbit with something like this. You see that the resolution, of course, not the same, but no averaging kernels to take into account. Then it's up to user to choose what it had to do. So we retrieve it for almost all the species, but for the ozone, it's already out there. It is already public. So the validation exercise. We compared with satellite instruments, ACE, HOMOS, MLS, AZARIS, SAGE, and SCIAMACHI. So for most of them, we are taking the matching criteria 500 kilometers in 5 hours, except for MLS. As both are dense samplers, we can allow ourselves the matching criteria to 250 kilometers in 4 hours. For the temperature, so the early MIPAS period we are comparing with HALO, with 5 hours mismatch, and the later MIPAS period we compare it with MLS with the same criteria as for ozone. And so we are using the latest version. So I was aware that there is a new version of ACE. Of course, I took it. Also the new version of MLS. But we also took the previous version just to compare apples with apples. The previous version of MIPAS was compared with the previous version of MLS. And there, just to see if there is improvement, we compared the same version of MLS with the new version of MIPAS. And we also take HOMOS, AZARIS, and SCIAMACHI from the latest release of the HARMAS data bank. In HALO version 19, I once tried to work with version 20. It was a nightmare. I don't understand. In the version 19, there is a problem with the uncertainty estimates, so I just don't use them. In the version 20, even the errors, even the values I don't understand. So by default, I work with version 19. So what it gives for the ozone. So here is the illustration of the comparison with ACE. So ACE is measuring ozone on always illuminated paths. MIPAS measures day and night, and at the altitude over 50 kilometers, the photochemistry is fast, and ozone can change due to the illumination quickly. So the first idea is to separate the day and night, but here there is a caveat in this, because when I say that, okay, we separate day and night by the solar zenith angle, but the question is solar zenith angle of what? So in the matched pairs, you have like MIPAS measurement and ACE measurement. So I'm taking it for the solar zenith angle of MIPAS, but within 500 kilometers and for 5 hours, you can have something like very different solar zenith angle. So by default, and this it's just an agreement if you want to choose. In this study, I'm saying that sample is day or night, as attribution to the sample is based on the MIPAS measurement in the matched pair. So here on the left, you see the scatter plot of the ozone with MIPAS day and ACE, and on the right, scatter plot of MIPAS night and ACE. So don't be too quick to attribute this bimodal distribution to the MIPAS non-LTA. It's not the fault of the MIPAS. Just we think that on this, it's just a bimodal distribution for the local sunset and sunrise ACE measurements. It will be just confirmed on the next slide by the histograms. So in the low panel, it's just so same for the day and for the night. So this is the panel, just matched profiles. So this is the bias, absolute bias, and this is the precision. For the day and for the night. Here are the histograms. So each column is a different height. So 27, 35, 60, and 82, no, 62, sorry. And so this is day MIPAS ACF, night MIPAS FTS. So night, yeah. Some co-authors advocate that we shouldn't even compare MIPAS night with occultation instruments, because those are always by default the day measurement, but well, this is a choice to make. So you see ACE starting from 60 kilometers, you see this bimodal distribution. This is which gives these two legs in the previous scatter plot. So this is a comparison with MLS. On the left, it's a comparison with the previous version of MLS of the new version of MIPAS and previous version of the MLS of the old version of MIPAS. So you remember we expected the improvement of the high altitudes. It's exactly what we constate here, because higher altitudes it's like bluish. You see here the bluish scatter is quite large. Here it is reduced. So we would say that there is improvement agreement of AirShare 8 at altitudes above 45 kilometers. So scatter plots for the first period of MIPAS, 2002-2004. So on the left day, on the right night. So for ACE, Azaris, SH2, and Skiamaki. So we see that, so it's just 3 years of data, so that's why there's not a lot of dots. So it looks quite reasonable, aside probably for the Skiamaki. So for the day, for the night, it looks quite reasonable for, I would say for all the instruments, except at the high altitude, but still it is reduced. I haven't included the plot here, but it is still is reduced compared to the previous versions comparison with COMOS. So here, for the day-night, we choose two panel plots. So on the left, you have the bias estimation, and on the right, we have what we call the residual variability. So basically, you just take the standard deviation of differences of the matched pairs, and you subtract the combined error of the instruments. And then we report it to the MIPAS and show in the percent. So actually, what is living here, these curves, this is a part which can be attributed to so-called natural variability. So it is for the day and for the night, for the 5 instruments. And so the part which is attributed to the natural variability, this can be refined. So there are some differences that cannot be explained by the combined error of the datasets. And the residual discrepancy is usually attributed to less than perfect collocation. So it's the natural variability because you don't sample the same air masses. But this natural variability, it was from the base code data, we did some estimation of the natural variability for over 30 species. And we can use these values just to refine a little bit the exercise and to see if there are still some unexplained differences in the data sets. So it is what is shown here. It is just a plot from the previous slide, but I added one curve here. It's a black curve. It's a black curve. So this is natural variability of ozone and 3060 north day in autumn. So basically, this refinement allows to conclude that in the season in these latitudes, so for MIPAS and MLS, for MIPAS and Azaris, so there is a good, for the MIPAS and MLS there is a good agreement, and for the other instruments probably sampling is not enough. So this especially don't blame ACE. I think this curve is such on the right from the left just because of the insufficient sampling. And no, I have like 1 minute for the temperature, but I have just 3 slides. So comparison of the early MIPAS of early period of MIPAS with HALO. So as I don't use the errors from the HALO, I can't do the estimation of the residual variability. So I just show the mean profiles and the bias. It is the first time that I'm doing the validation of the temperature. I was amazed how good the values are in the zone. I've never seen such a values. So still, so it agrees quite good. And for the night measurements, the same argument as before for ACE is applied. So should we really compare MIPAS night measurements with this occultation instrument? Not clear. So this is a comparison of the later MIPAS period with MLS. Also, the agreement is quite good, aside probably here. And the comparison with the radio occultation instrument Cosmic. So when I've seen this post, I saw that there is a like bug in the routine. I've never seen such an agreement, but well, still. The MIPAS temperature is known to be good for all 4 processors, but when you look at the values, I was amazed. So to conclude, actually there are we compared to satellites ozone zone I haven't shown here in the radio occultation, the MIPAS ozone and the temperature record from the EMK processor. So expected improvement on ozone profiles at the high latitudes is confirmed. We have MIPAS actual the temperature record remains of the excellent quality, so the uncertainty I within 2K, and it greens with MLS at some at 50.43, HALO at 8.42, and Cosmic at 70.39 almost perfectly. And also we demonstrated how the further refinement of the validation exercise can be done using the fields of the natural variability that we calculated from the BASCO. So there are still some discrepancies that are not explained, but this time you just don't dare anymore to say this is natural variability. No, it's not. It's something still in the instrument record. And that's all.